Welcome dear students. I'm Dr. Neelam Yadav from ABES Engineering College. This lecture video is in continuation to the previous lecture video on atomic and molecular structure, where we have discussed about the postulates of molecular orbital theory. The content which will be covered in this lecture video is the applications of molecular orbital theory, which will be including the molecular orbital diagram of homodiatomic molecules and heterodiatomic molecules. To initiate with the lecture video, I'll be discussing few points of the postulates of molecular orbital theory, which will be helpful in making the molecular orbital diagram of various molecules. In postulates, we have discussed that for lighter molecules, that is molecules from hydrogen to nitrogen, we were following the type 1 of configuration for molecules. This type 1 is if the number of electrons in the molecule is less than equal to 14, then the molecule will have the configuration of sigma 1s, sigma star 1s, sigma 2s, sigma star 2s. Then the pi 2px orbital will be at this energy level, pi 2py at equal energy levels, then sigma 2pz. And for antibonding, we will be having pi antibonding 2px and pi antibonding 2py at equal energy levels, and then we will be having sigma star 2pz. The star mark is denoting the antibonding orbitals, and the other one is denoting the bonding molecular orbitals. For the molecules which are ranging from oxygen to fluorine, the sequence which is followed is type 2, and in this case type 2 involves number of electron in the molecule is greater than 14. Then the sequence electronic configuration for the molecule will be sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, and here the energy level of pi bonding and sigma bonding will interchange. So here it will come sigma 2pz, pi 2px, pi 2py, and for antibonding it will remain the same, pi star 2px, pi star 2py. This energy sequence is calculated by using the spectroscopic techniques. Now we will be taking an example of molecular orbital diagrams for homodiatomic molecules. Homodiatomic molecules are the molecules which are having both the atoms are same. Like we can take an example of H2, O2, O2 plus. These are the ions and molecules. Now, how we make the molecular orbital diagram for these molecules are, initially we will take a simple example. We are taking an example of H2 molecule. This H2 molecule is made up of two atoms, one hydrogen atom and another also hydrogen atom, because they are homodiatomic molecules. The atomic number of hydrogen atom is 1 and the configuration of atomic atom is 1s1 and 1s1. When this forms the molecules, the number of electrons in the molecule is 2 and this will follow the type 1. So the sequence of energy will be sigma 1s, sigma star 1s. Now when we prepare the diagram, we are taking approximately 3 columns. 2 columns in the sides are of atomic orbitals, and the center column is of molecular orbital. So this is atomic orbital of first hydrogen atom, and this is atomic orbital of second hydrogen atom. And in center, we are making the molecular orbital of hydrogen molecule. Now, this atomic orbital of first hydrogen atom is 1s, and it is having 1 electron. So we will be giving 1 electron to this hydrogen orbital. And this hydrogen atom is also having an orbital of 1s1, and this is the electron being given to the atomic orbital of second hydrogen atom. Now, when these two atomic orbitals combine, now since two atomic orbitals are combining, they will be forming two molecular orbitals. One molecular orbital will be sigma 1s, and the other atomic orbital will be sigma star 1s. Now filling the molecular orbitals, since total electrons present in both the atoms are 1 and this is 1, 2. So this 2 will be filled from lower energy level of the molecular orbital. Sigma 1 is having lower energy. So initially we will give 1 electron to this molecular orbital, and we are having one more electron, and this orbital is not completely filled. So the second electron will also be given to this sigma 1s. Now since we are not having any other electron left, so this sigma star 1s orbital will be empty. As we move upward, the energy of the molecular orbitals increase. This is how we are preparing the molecular orbital diagram for homodiatomic molecules. Now with this molecular orbital diagram, we can also calculate the bond order of the molecule. Bond order is given by number of bonding electrons minus number of anti-bonding electrons divided by 2. Number of bonding electrons for hydrogen atom is this. This is the bonding electron. So here we are having 2 bonding electrons minus number of anti-bonding electrons for hydrogen atom. Hydrogen molecule is 0. 2 minus 0. This will be giving 2 by 2, which is 1. So the hydrogen molecule will have a single bond between the two atoms. While discussing the magnetic behavior for this molecule, we will check the molecular orbital diagram. If all the molecular orbitals are having paired up electrons, then the molecule is said to be diamagnetic. In this case also, the molecular orbital is having completely filled or paired up electrons in its molecular orbital sigma 1s. So this is how we prepare the molecular orbital diagram for hydrogen molecule. Now we'll be taking another example where there is p orbital is also there. We will be taking an example of O2. This is also formed by 2 oxygen atoms. The atomic number of oxygen atom is 1s8, sorry, and the configuration is 1s2, 2s2, and this will be 2p4. Similarly, for this oxygen atom also configuration will be 1s2, 2s2, and 2p4. For oxygen molecule, the total number of electrons will be 8 plus 8, 16. This is greater than 14, and this will follow the type 2. And as previously discussed, the configuration which is given for type 2 is sigma 1s, sigma star 1s, sigma 2s, sigma star 2s. Now here comes sigma 2pz, pi 2px, pi 2py, pi star 2px, pi star 2py, sigma star 2pz. Now, while preparing the molecular orbital diagram, similarly, we will making the columns of atomic orbital. One atomic orbital is oxygen, and the other atomic orbital is also oxygen. This is homodiatomic molecule, and in the center we will be representing molecular orbital, that is O2. First atomic orbital for oxygen atom is 1s. In case of homodiatomic molecules, when we are making the atomic orbitals, these atomic orbitals should lie on the same line. Their energy level should be same. And for bonding molecular orbital, the energy will be lower to the atomic orbitals, and for antibonding, the energy will be little higher to the to the atomic orbitals for antibonding molecular orbitals. In this case, 1s is having 2 electrons. So one positive spin, one negative spin. Similarly, this oxygen atom is also having 2 electrons, one positive spin and one negative spin. When these two atomic orbitals will combine, they will form two molecular orbitals. One will be sigma molecular orbital, sigma 1s, and the other molecular orbital will be antibonding sigma star 1s. Now filling up the molecular orbitals, since the number of electrons by combining these two atomic orbitals will be 4. So initially we will be giving one electron to the sigma molecular orbital, and then we will be giving another electron to this orbital because we are having electron, and this is this sigma 1s or bonding molecular orbital is not completely filled. Now this is completely filled and we are still having 2 electrons, so that electron will be given to the antibonding molecular orbital. Now we are combining the 2s orbital of atomic orbitals of oxygen, 2s2, and this will be in the same line, 2s2. These two atomic orbitals will also give two molecular orbitals, one bonding and the other one will be anti-bonding. They are also having 2 electrons, atomic orbitals. So they will be given 2 electrons each. Now in total, there are 4 electrons in 2s of oxygen atoms. So molecular orbital will be filled up with this 4 electrons. 2 will be given to the bonding molecular orbital, 2 will be given to the anti-bonding molecular orbitals. Now we will combining the p orbital of oxygen atom. X, P, Y, P, Z, P, X, P, Y, P, Z. We have seen the configuration. Here sigma 2pz is having the lower energy, and then the energy is of pi 2px and pi 2py. Now for antibonding also, pi star 2px and pi star 2py, and then comes sigma star 2pz. We have made the orbitals for atoms as well as molecule. Now we will be filling the electron. Since p orbital of oxygen atom is having 4 electrons, so initially we will be giving single electrons to px, py and pz, and the 4th electron will go to any of the px, py or pz orbital. In second oxygen atom also we will be doing the same thing. This is Z, sorry. Now we'll be filling the molecular orbitals. In total, electrons present in p orbital are 4 of one oxygen atom and 4 of other oxygen atom. There are 8 electrons. So we'll start filling from lower energy of molecular orbital of p. So 1, 2. Now for px and py, initially we will be giving single electrons, 3, 4, 5, 6, then we will go to above antibonding orbital 7, 8. Now this is how we are preparing the molecular orbital diagram of oxygen molecule. Now to calculate the bond order, we have the formula number of bonding electrons minus number of antibonding electrons by 2. Now this will be giving number of bonding electrons are, here it is 2, 4, 5, 6, 7, 8, 9, 10. So we are having 10 bonding electrons, and for anti-bonding we are having 2 are here, 2 at sigma star 2s, and for pi star 2px and pi star 2p5 there are single electrons. So we are having in total 6 anti-bonding electrons divided by 2. This will be given as 4 by 2 and 2. Now the oxygen atom over here will be having double bond between 2 atoms, oxygen molecule. Now for magnetic behavior, we'll be checking the molecular orbitals of oxygen molecule, and we are seeing that pi star 2px and pi star 2p5 is having unpaired electrons. So the magnetic behavior of this oxygen molecule will be paramagnetic. Now we will be discussing about some of the ions of this oxygen atom and what configuration they will be following. For instance, let's take the ion of oxygen atom. We are taking over here O2 minus, O2, 2 minus, O2 plus, O2, 2 plus. Now for O2, 2 minus, the total number of electrons will be, since one electron is added, so total number of 2. Since as we know, O2 is having total number of electrons 16. So it is following the type 2. Now O2 minus will have total number of electrons 17. This is greater than 14. This will also follow the type 2. O2 2 minus will have the total number of electrons 18. It will also follow the type 2. Now O2 plus is having the total number of electrons 15. This will also follow the type 2. Now O2 2 plus is having the total number of electrons 14. Now in this case, what actually we have discussed is it must follow type 1 because it is having total number of electrons equal to 14 and the configuration of type 1 is different. But for molecules and their ions, all will follow the type which the parent molecule is following. So the parent molecule over here is O2. So whichever type O2 will follow, its ions, all the ions will follow the same type. And while preparing the molecular orbital diagram, what we have to do is, for instance, we are making the molecular orbital diagram of O2 minus. Then one electron will be added to molecular orbital diagram. One electron we can add over here. One electron will be added to one electron. For O2 minus, one electron will be added here. For O2 2 minus, one electron will be added over here. At one electron will be added over pi star 2py. In case of O2 plus, when we are talking about O2 plus, then the electrons will be removed. In O2 plus, we are having 15 electrons, so we will be filling only one pi star 2px. Similarly, for O2 plus, we can make the molecular orbital diagrams. Now for molecular orbital diagrams application or molecular orbital theory application for heterodiatomic molecules. Heterodiatomic molecules are the molecules which are having different atoms in the molecule. For example, NO, CO plus, HF. These are some of the heterodiatomic molecules. In this case, the molecular orbital energy level of the more electronegative atom of the two is skewed towards the bonding molecular orbital. Or we can say that more electronegative atomic orbital lies closer to the bonding molecular orbital and less electronegative atomic orbital lies closer to the antibonding molecular orbital. While preparing the molecular orbital diagram for these molecules, for instance, we are taking an example of NO molecule. There is a slight difference of preparation of molecular orbital diagram for heterodiatomic molecules. Here, two atoms are N and O. This is having 7 atomic number. This is having 8 atomic number. Their configuration is 1s2, 2s2, 2p3. This will be having 1s2, 2s2, 2p4. For NO molecule, the total number of electrons is 15. This will follow. This is greater than 14 and this will follow the type 2. Configuration for type 2 is sigma 1 is, sigma star 1 is, sigma 2 is, sigma star 2 is, sigma 2pz, pi 2px, pi 2py, pi star 2px, pi star 2py, sigma star 2pz. While preparing the molecular orbital diagram over here, we have to take care that atomic orbital of, for instance, this is the atomic orbital of nitrogen and this is the atomic orbital of oxygen. The more electronegative atom will have its molecular orbital close to bonding molecular orbital and the less electronegative atom will have its atomic orbital close to anti-bonding molecular orbital. So here the level of atomic orbitals will be different. More electronegative will lie towards or near to the bonding molecular orbital and the less electronegative atom will lie towards the anti-bonding molecular orbital. Now filling up this electrons, one is nitrogen atom, oxygen atom, this is atomic orbital, this is molecular orbital, NO. 1, 2, and this will be also. Now similarly, 2 is of nitrogen atom will be here and 2s will be of oxygen atom will be at lower end or near to bonding molecular orbital. So this will be filled like this. For p orbital as well. In case of oxygen, it will be a bit lower. This is Px, Py, Pz, Px, Py, Pz, Px, Py, these are forming pi, and this will be forming sigma 2p z. And for antibonding, pi star 2px, pi star 2py, sigma star 2pz. Now filling up the electrons, we have not filled over it. For p orbitals, total number of electrons is 4 for oxygen atom, 4 and 3 for p orbitals for nitrogen atom. So 4 plus 3, there will be 7. We will be filling up from lower energy. 1, 2, 3, 4, 5, 6. And here goes. Now, when we are talking about the bond order calculation, bond order is equal to number of bonding electrons minus antibonding electrons upon 2. Bonding electrons over here are 4, 5, 6, 7, 8, 9, 10. Minus antibonding are 5 upon 2. This is 2.5. For NO, the bonding orbital is 2.5 and the magnetic behavior is paramagnetic. Since pi star 2px is having unpaired electron. If we will be making the molecular orbital diagram of its ions, the type followed by these ions will be type 2. That means the configuration which is given over here will be followed by the NO plus as well as NO minus molecules. Now, next example we are taking over here is CO. There is a slight difference in the molecular orbital diagram of CO. Carbon plus oxygen. Carbon is having 6 electrons. It is having 8 electrons. 1s2, 2s2, 2p2. This will be having 1s2, 2s2, 2p4. Configuration over here is slight difference. Let's make the diagram. Since they are heterodiatomic molecules, the atomic orbitals of carbon and oxygen will not lie on the same line. So oxygen atom will be lying a bit closer to the bonding molecular orbital. So sigma 1s, this will be forming sigma star 1s. Since the electronegativity difference between carbon and oxygen is comparatively more than that of NO, the diagram formed for CO is slightly different than NO as well. In this case, the antibonding of 2s orbital lies somewhere above the bonding molecular orbital of 2p. So here we are making 2p as well. In case of carbon, 2p orbital is having 2 electrons, px, py, pz. For oxygen, now here what happens? Since 6 plus 8, it is having 13, type 1. It is following type 1. In case of type 1, we are having pi px below and sigma 2pz. And in case of CO molecule, sigma star 2s lies above sigma 2pz. So here it lies sigma 2p. Filling the electrons, and for antibonding pi orbital, it is the same sequence. Pi star 2px and pi star 2py will be below and sigma star will be above. Now filling up 2s orbital, carbon atom is having 2, oxygen atom is also having 2. There are 4 electrons, 1, 2, 3, 4. And here there are 4 plus 2, 6 electrons. So 1, 2, 3, 4, 5 and 6. This is the configuration for CO molecule and the diagram for CO molecule. Bond order. number of bonding minus number of anti-bonding upon 2. Bonding electrons are sigma 1s 2, sigma 2s 2, 4, 9, 10. Anti-bonding are 4 upon 2. This will form 6 by 3. This will. So CO molecule bond order is 3. And magnetic behavior will be, since all the molecular orbitals are completely filled, magnetic behavior will be diamagnetic. This is the molecular orbital diagram for CO. And if we are preparing the molecular orbital diagram for CO plus, in that case, one electron is being removed. For CO plus, one electron is being removed. So one of the electron from oxygen atom will be removed, and here it will be having one electron, and the magnetic behavior of the CO plus molecule will be paramagnetic. Now we're taking another example of heterodiatomic molecule, that is HF molecule. In this case, the electronegativity difference between the hydrogen and the fluorine is very high, and here also the diagram being made is quite different. So the diagram will be for fluorine atom, or for, we can consider like for hydrogen atom. The 1s orbital of hydrogen atom, energy level of 1s orbital of hydrogen atom is somewhat near. Let's write the configuration of atoms. 1s1, 1s2, 2s2, and this is 2p5. So the energy of 1s orbital is somewhere near to the energy of 2p orbital of fluorine atom. Since the electronegativity difference is quite high between the hydrogen and the fluorine, so here it forms 2p orbital. 2s, and this is 1s. This is atomic orbital of fluorine. This is atomic orbital of hydrogen. And in center, we'll be preparing molecular orbital of HF. So since 1s of fluorine is not participating in bonding, so this will form non-bonding molecular orbital. Since 2s is also not participating in bonding, it will also form non-bonding orbital. This is 2p. This will be having 5, 1, 2, 3, 4, 5. And hydrogen atom is having 1s electron. From p orbital, one of the suborbital of p combines with the s orbital of hydrogen, and it forms sigma sp bond. And the other two suborbitals of p, since they are not participating in bond formation, they will be forming non-bonding orbital. Since one s and one p orbital is combining to form bond, it will form two molecular orbitals, one sigma sp and the other will be sigma star sp. So now here we will be calculating the bond order is number of bonding electron minus number of anti-bonding electron upon 2. Here number of bonding electron is only 2, because 1s, 2s and 2px and 2py are still are not are non-bonding electrons. So here we can calculate the bond order as 2 minus antibonding electron is 0 upon 2. This will be giving 2 by 2, which is 1. So HF molecule will have single bond. Here it is PX, PY, and this is PZ, which is participating in the bonding. Its magnetic behavior will be diamagnetic, since it is having paired up electrons in the molecular orbital. So this is how we are making, or the molecular orbital diagram for heterodiatomic molecules can be prepared. These are some of the references. Thank you.